Okay, so today we're going to start a little lesson on work and energy. This is Unit 2 in physics. But first we're going to do a quick little review. We've done this a couple times, but just to get you thinking again, because these are the more challenging problems. When you're dealing with a ramp and the geometry of a block on a ramp and the physics involved, what you just got to keep in mind is keep your x-axis parallel to the ramp, keep your y-axis perpendicular, and then everything should work out nicely. The problem comes because what you're talking about is three sets of forces. So if you have a block sitting on a ramp and friction is holding it there, the forces are not all mutually perpendicular, and that's why this becomes a more challenging problem. So the idea, though, is to just take one of those forces and break it into components that are perpendicular. And we choose to do that to the gravity component. So we have the gravity component, and we're going to break it down into the x direction. So we're starting the x direction is going to be parallel to the ramp. And if we want to do a sum of all the forces in the x direction, we have that friction force that's going uphill, and then we're going to have the component of gravity that tends to pull it downhill. And the sum of those forces, if this thing isn't moving, for example, would be equal to 0. If the block is moving, then you would set it equal to mass times acceleration. So it just depends on the problem. But the point is, you have to come up with the force component being, and I'm talking specifically about this component of gravity here, that tends to pull it down the hill, and then put that in the x direction. And then we look at the y forces, and so we have the normal force pulling up, but then we also have the component of gravity that is tending to hold the block against the ramp. In other words, it's kind of opposite the normal force. Now we know that the block is not accelerating through the center of that ramp, and so we can set up all the forces. Some of the forces in the y direction is going to be equal to 0. So we have the normal force pushing up, I'm defining up as positive, and then we have that component of the gravitational force that is holding it against that ramp. So now we could solve the problem, set the normal force equal to mg cosine theta, and solve. So that's just a little bit of geometry review as it becomes useful as we go forward. Okay, now let's get into work. What is work? In physics, the definition of work is very different from what we have in everyday language. So, in physics, we would say that you could climb a mountain and climb back down, and you will have done no work. If you take a 200-pound barbell and you move it horizontally, then you've done no work. And if you complete a 2-hour-long homework assignment, you have definitely not done any work. So, obviously, physics is a different definition that you're used to. Here's the good news. Work is a scalar. It is not a vector. So we don't have to worry about magnitudes and directions. We don't have to worry about breaking things into components. It's just a scalar. It's a magnitude. It has a value. We just add it up. Now, we can't have negative values. You can have negative work, so we'll talk about that in a minute. But at least we don't have to do anything with components. Work is a precursor to energy. We're going to start talking a lot about energy throughout this year, and especially in the next couple of weeks. The units for energy, the SI units, is a Newton times a meter, and that is such a common unit. It has its own special name, and it's called a joule. And we'll talk about James Prescott Joule and his important discoveries when it comes to energy pretty soon. Okay, so what is work in a physics sense? Work is applying a force over a distance, or force times displacement. So if you take something and you push it for a given displacement, that's going to determine how much work you've done. What we say is that work is positive if the force that you apply is in the same direction as the motion that the thing moves. And that's typically what makes sense, right? If you have a little block and you push it and it goes a certain distance, you've done positive work. Negative work is when the force is acting in the opposite direction as the displacement. And so a common example of negative work would be like if you shove a block and now it's moving, but then it kind of slides to a stop because friction is acting in the opposite direction as the displacement. So the thing moves to one direction and friction is acting in the opposite direction, tends to slow it down. So you usually get negative work from friction. Okay. What if you want to work against gravity? So here's just an example. Let's say you're lifting an object. So you have a barbell, and a person, in order to lift an object, is going to have to apply a force. And the force of holding that object, just holding it steady, the force they have to apply is mg. They have to apply basically the opposite force of the gravitational force that is acting on the barbell. So to hold it, you have to apply a force mg. And then if you want to move it, So here's your force. If you're going to move it up this direction, then you're going to do work on it. Your force is mg, and it's in this upward direction, and the displacement is also up, so you would do positive work. So you say that a person is going to do the work of mg times that height that you lifted. So that's the distance or the displacement. Okay? So that's the person doing work. Now, if you've lifted up the barbell and now you bring the barbell back down again, and we say, well, can gravity do work? Well, if we think about gravity doing work, as the barbell comes back down, okay, then gravity, what direction does gravity act? Gravity is pulling down as well. So gravity, as the barbell comes down, is actually acting in the direction of displacement. So then gravity can do work. So as the barbell comes down, we say that gravity is doing positive work. Sometimes it's helpful to think about components. Like if you're going to mow the lawn, it would be really efficient to mow the lawn by pushing this way, but that's not really practical from a person's perspective who's standing up and trying to mow. So what you need to do is have your lawnmower kind of bent at an angle. Except that work is defined as the force that's applied in the direction of motion. So we have to get the component of force that is in the direction of motion, not the entire force. So what we do is we take that force vector and we're going to break it into a component. And we're going to find out what component of the force is parallel to the direction of motion. And it turns out that we can find that because that force is F cosine theta. So this force that's parallel is F, this total magnitude of the force, times the cosine of the angle between it. So we have a more general definition for work. Instead of just force times displacement, we say it is F d cosine theta, where F is the force that's applied, d is the total distance traveled, and then cosine theta. Theta is the angle between the force vector and the direction of motion. Okay, so it's going to be right there. Okay, so that's the idea. This basically says what we just said. If the force is applied perpendicular, so that's kind of interesting. Like if you had your little lawnmower and then you applied a force straight down, okay, and you wanted to move the distance this way. Well, you get a sense, right, that if you apply a force down, it's not going to actually move. There is no horizontal component of force. It's actually not going to move in this direction. In fact, if you find this angle, that angle is going to be 90 degrees, and the cosine of 90 degrees is actually 0. So that means that if you apply a force perpendicular to displacement, it won't do any work. So an example of that is if you have a barbell and you are holding it, remember you're going to be applying a force up to hold it, okay, so the force is going to be up as you hold the barbell, but then if you move it horizontally across the floor, then you say that you've done no work because the force that you applied of holding it is not doing any work. Now there might have been a little work to move it to the right, but that force of holding it up, which is opposite the gravity force, is not going to be doing any work. Okay, so what is the net work in lifting a barbell? When I say net work, I mean like what are all of the things that are applying forces to the barbell? How much work do they each do? Okay, so if you think about this, the person we talked about before, if I'm going to take it from down here and I'm going to lift it up, okay, the person's going to do work of mg, that's the force, times the height. Okay, so you got mg, that's the force, times the height. That's the work the person does. But what about gravity? While you are lifting it up, gravity is pushing it down, right? And then the displacement is going to be up again, so that's the displacement h, and gravity is pushing it down. So in this case, the angle between these two, so if you say here's mg and you say here's h, the angle between is going to be 180 degrees. And so the cosine of 180 is -1. So you say that gravity is going to have the work of mg times h, but it's going to be negative because of that, because they're acting in opposite directions. So if you add up those two together, in lifting a barbell, the net work, meaning all of the work done both by the person and by gravity, is 0. Another network problem, so let's say we have a block. This is kind of a typical quantitative problem. We have a block and we want to slide it to the right. So it's going to start here, and it's going to go a total of 10 meters to the right. What is the net work that is done on the block? We have two forces acting on it. We have a 50 Newton, that might be like a tension force right here, And then we have a 10 Newton friction force. So as you're pulling it along, the friction is always going to be acting in the opposite direction. So the net work is just going to be the work of the friction plus the work of the tension force. So here's your tension force, right? It's going to be 50 newtons, because it's to the right, times 10 meters, and then the angle between them is 0 degrees. So that's cosine of 0 degrees is 1. So that's going to be a total of 500 joules. And then we have the friction force, and the friction force has 10 newtons, and the total displacement is 10 meters, and then the cosine of the angle. Now, because these are in opposite direction, you have 180 degrees, and so that's going to be a total of -1. So you get 10 times -1, and you get -100 joules. Then to get the net work, you just add them up. So when you're doing net work problem, you just look at each force and each displacement and the angle between them, and you add them up. They're scalars, which makes it really easy. So then you see this ramp problem, and you might worry about the fact that you have a ramp. But not to worry, because with work, we're dealing with scalars, so it's really not that bad. So let's check it out. Here's a problem. A 4-kilogram block is pulled, so here's our block down here, and it is being pulled up the hill by a rope for 2 meters along a frictionless ramp inclined at 40 degrees. Okay, so we don't have any friction to worry about, so that's one force we don't have to think about. The rope parallel to the ramp has a tension of 30 newtons. Find the work done by tension, gravity, and the net work, in other words, the total work. Okay, so we're going to break it down. We're going to look at each force individually and consider how much work is done. So here we go. Let's start with the work done by tension. Okay, the work done by tension. So that's going to be the tension force, which in this case is 30 newtons, times 2 meters, that's the distance, the displacement, okay, times the cosine of 0 degrees, because those are in the same direction. The displacement is in the same direction of the force, that angle is 0 degrees, and so we just solve and we get 30 times 2 times 1, which gives us 60 joules. A Newton meter is a joule. All right, next we're going to find the work done by gravity. Okay, now gravity is going to be the force of gravity, and then the displacement again is 2 meters, and then the angle. What is the angle between the force that is applied, that gravity force, and the displacement? So check it out. If this angle is 40 degrees, then that angle has to be 140 degrees. So we just say times the cosine of 140 degrees. That's it. You don't have to break it into any components. You just find the cosine, because you got FD cosine theta. So there we go. We can now solve that. 4.0 kilograms times 9.8, that's the gravity force, times 2 meters, times the cosine of 140, which is a negative value, and that makes sense, right? Because the work of gravity is acting against the direction of motion, so it's going to kind of take away from the total work, so that makes sense. It would be negative. And then that's going to be total of -60 joules. Now, just there's total coincidence that those two values are exactly the same. If I'd made the tension force 40 newtons, then they would have been different, but coincidentally, they're the same. Now, what about the normal force? The normal force, what work does a normal force do? So you have to find the magnitude of the normal force times 2 meters times the cosine of the normal force to the displacement. Now, here's the good news. Cosine of 90 degrees. Perpendicular forces, or forces perpendicular to direction of motion, don't do any work because they don't get it to move. There's no component parallel. So that work is going to be 0. So the total work for the entire scenario is just the tension work and the gravity work, because the normal force work doesn't contribute. Okay, moving on. Energy. So we're going to be talking about some different types of energy. Work we've defined as FD cosine theta. It has energy units of joules. And then we're going to get into mechanical energy, specifically kinetic energy, gravitational potential energy, and elastic potential energy. We're going to start with kinetic energy. Well, it turns out that if we understand what's going on with work, where you add up all of the forces times the displacements, okay, so if you take the net work is the sum total of every force times every displacement, and you do a little bit of calculus, okay, it's not complicated at all, but a little bit of calculus. If you recall, if you've done calculus, the summation is like an integral. If you've never had calculus, don't worry about it. But with a little bit of calculus, there is a derivation that will show you that the net work, if you add up all the force times the displacements, is equal to m times the final velocity squared of an object minus the initial velocity squared of an object. And we can rewrite that term to look like this. And this is a really kind of famous expression, or I should say, at least if you isolate this, okay, this idea of 1/2 mv squared. That's a really important concept. What we say is that this represents the change in kinetic energy. Okay, I'm going to say change in kinetic energy. And specifically, kinetic energy is represented by this value right here. So let's move on. Kinetic energy is defined as the energy associated with a moving mass. So Ke is 1/2 mv squared. Units, if you work it out, mass, kilogram, times meter squared per second squared gives you newton meters or joules. So we get energy units just like we did with work. Okay, 1/2 mv squared is one of those expressions you're going to remember, and we're going to use it throughout this entire year in physics. So example, calculate the kinetic energy of a Madison Bumgarner fastball. If the mass of baseball is 0.145 kilogram, he can throw it at 41.6 meters per second, which is about 93 miles an hour. Then you just say 1/2 mv squared, 1/2 times m times v squared, and you get about 126 or so joules. So you'll be doing some calculations like that. Okay, this is a little video. You're not going to get to see it because it's a recording, but I have a little puppy dog, and if we slide her along the floor, she'll come to a stop. So here's the idea. If I have a Scout is my puppy, sliding on the wood floor, she's not a puppy anymore, she was then, but now she's 7 years old. If you slide her on the floor with a velocity of 4 meters per second, what is her change in kinetic energy as she comes to a stop? I'm going to say the mass of Scout is about 5 kilograms. So we say the change in kinetic energy is 1/2 mv final squared minus 1/2 mv initial squared. Well, her initial velocity is 4 meters per second, and her final velocity is 0 because she comes to a stop. So what is the change in kinetic energy? Well, 1/2 times 5 times 0 squared minus 1/2 times 5 times 4 squared, with a total of 40 joules. So she has lost 40 joules. And if you're curious, like, where did the energy go? Well, it kind of heated up the environment, but basically friction. Friction was acting on her and did negative work, and that negative work was ended up causing a loss of kinetic energy. Okay. Another kind of energy is gravitational potential energy. Okay, potential energy is energy that is stored. It's like ready to be used. It has potential. So we're ready to convert potential energy into some other useful energy. It is the energy of an object due to its position relative to the Earth. Okay, and you'll see that in the next little picture that I'm going to show you. When you're talking about potential energy problems, it is safe to assume that G is constant, gravity. Okay, now if you are doing a potential energy calculation of a satellite that blasts away from the Earth, then you might have to consider the fact that gravity actually changes as you get further away from the center of the Earth. But for our all intents and purposes in these problems here, you can assume gravity is constant. The units for potential energy, just like kinetic, is newton meters or joules. So here's the idea. Coyote here is up on top of a cliff, okay, and Coyote has what we would say potential energy. In other words, it's like he did all this work. Like if he was standing next to Roadrunner and he climbed all the way up here, okay, now he has a whole bunch of energy stored, because you know that if he stepped off that cliff, he would start to fall, and his potential energy would actually get converted into kinetic energy. It would be moving really fast. So that's really interesting. Well, how much energy does Coyote have? Well, the way we talk about it is we say, measure some arbitrary 0 point. You get to decide. And usually people will typically say, we're going to have the 0 at the bottom, and then he climbs up a height h. And so if he climbs up a height h, then he has a total potential energy of mg times h. And you just choose a 0 to be convenient. So, for example, a 200 kilogram boulder is poised to fall on Roadrunner 50 meters below. What is the potential energy with respect to Roadrunner? Okay, how much energy does this boulder have? Okay, well, it's just mgh. M, and make sure your masses are always in kilograms. M times g, 9.8 meters per second squared, times h, 50 meters. For a total of about 98,000 joules. So that's a lot of energy that you could convert, and actually it's going to get converted into kinetic if you launch it off that cliff. Another type of energy is spring energy, or stored energy. If you pull apart a tight spring, you are storing energy in that spring, and if you let go of the spring, whoosh, it's going to release that energy. So we say that we talk about potential energy stored in a spring. this is the more physics concept here. The idea is this. We have an equilibrium position. So here is your equilibrium position. If you have a spring and it's just hanging out, this is a horizontal spring. So it's a horizontal spring that kind of goes wah, 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 back and forth, back and forth. So if we say this is an equilibrium position, this is where the position would be if it's just at rest. But then if we squish it, so if we compress it, if we push it this way, then you're going to have a compressed spring, and if you let go, whoosh, it's going to take off and go that way, right? Or if you take the spring and you stretch it out this way and you let go, whoosh, it's going to go back. So by displacing the spring from its equilibrium position, you're building in potential energy. And eventually you could release that thing and then woof, it's going to move. So it's going to convert from potential to kinetic, basically. Now, how do you quantify potential energy stored in a spring? Well, we have this lovely formula. Potential energy of a spring, and I say K, that stands for spring because springs have what we call spring constants. And a spring constant represents the stiffness of the spring. So a big spring constant means you have a really stiff spring. Spring constants have units of newtons per meter. So if you want to know how much energy is stored in a spring, go 1/2 times K, that's the spring constant, times x squared. And x represents that distance that has been separated from the equilibrium position. So if you pull it 3 centimeters, that's going to be your x value. Okay, so we'll look at an example problem. Here we go. A spring with a force constant of 6 newtons per meter, that's K, has a relaxed length of 2.5 meters. When you attach a mass, it stretches to 4 meters. Find the elastic potential energy stored in the spring. Okay, take it up, take a look. We have a regular spring and it's stretched out. This is a vertical spring and it's about 2.5 meters when it's fully extended. And then we add a little mass to it, and so now it stretches out to 4 meters. So think about what the equilibrium position is and then what the stretched position is. That total stretch position is going to be 1.5 meters. So there's your x value. Okay. Then the question is, find the elastic potential stored in the spring. Okay, so remember our formula. We have potential energy is going to be 1/2 kx squared. Now, the spring constant we decided was 6 newtons per meter. So 1/2 kx squared, that's our spring constant. And then we have 1/2 times that k times 1.5 meters squared. And that's going to give you the total amount of potential energy that you have stored in your spring. Okay. Couple concept questions, actually just one or two. Molecule A has 4 times the mass of molecule B, but they have the same kinetic energy. Find the ratio of B's speed to A's speed. Okay, so you have one molecule, so like molecule A is really massive, okay, and molecule B is not so massive, and molecule A has 4 times the mass of molecule B. Okay, the question is, if they have the same kinetic energy, what's the ratio of their 2 speeds? Now, it makes sense if they have the same kinetic energy, and this one is really massive, that this one must be moving really fast. So let's find out how fast. Okay, so we'll write a little equation. Here we go. We'd say that the mass of A is equal to 4 times the mass of B. That was given. Okay, and we know that the kinetic energies are the same. So we say 1/2 the mass of A times the v of A squared equals 1/2 the mass of B times the speed of V squared. That's the kinetic energy of each one, and they are equal. All right, so let's find the ratio of their speeds. The 1/2s cancel. We're going to bring VB on one side and VA on the with it, and then we're going to get VB squared over VA squared equals MA over MB. So far, so good. But what we really want is the ratio of the speed, not the square of the speed. So let's square root both sides. Actually, first of all, I'm going to substitute the 4MB in for the MA, right? So we get everything in terms of MB. Then my MB's cancel. Sorry. So VB squared over VA squared equals 4. Now I can take a square root. And I can get VB over VA is the square root of 4, which is 2. Or the ratio is going to be 2 to 1. So in other words, B has to be going twice as fast as A in order to have the same amount of kinetic energy. And that makes sense, right? Because this equation is more reliant on the speed. It's the speed squared. So the speed is going to play a greater role in providing kinetic energy than the mass. All right, that concludes our lesson. Good luck.